Thanks for joining us for another edition of Alaska Weather Facts. I'm meteorologist Dave Snyder, joined again by Eric Stevens from the GINA, or Geographic Information Network of Alaska at the University of Alaska Fairbanks. Thanks for joining us again, Eric.
Glad to be here.
Thanks. We are talking about satellites today, and what are satellites? And the easy way to talk about that would be to introduce our friend the globe here, which is a round spheroid type shape. We haven't been on a flat Earth as far as history is known for several hundred years now, and because of that we also know that we are orbiting around other objects in space, and that objects are orbiting around the Earth as well. We call all those things satellites in some form or fashion, right, Eric?
Right. Well, this leads to the discussion of Johannes Kepler's research 400 years ago. Did some of the early work and founded the 3 laws of planetary motion, which are important to planets and also to weather satellites.
Okay.
Kepler's first law talks about how the orbit of an object around another object is an ellipse, not necessarily a circle.
Kind of a flattened circle?
Yeah, depending on how flat
squished
it could be.
Okay.
For our purposes, we'll just say they're mostly circular.
Okay.
The second law is most important for us, though, and that is the closer an object is to the thing it's orbiting, the faster it goes. So in the solar system, the planet Mercury is the closest planet to the sun. It orbits the sun in 88 days. It moves at 100,000 kilometers an hour.
It is just
moving.
Okay.
Right. And further out from the Earth is Jupiter, and it moves at only 1/4 the speed of Mercury, and it has to go further, so it takes 12 of our years for Jupiter to make 1 lap. The further out you are, the slower you go.
Okay.
So we're talking about planets. What does it have to do with weather satellites? Turns out Kepler's laws apply to planets orbiting the sun. They also apply to satellites orbiting the Earth.
Okay.
You know, our natural satellite is the moon. There's the famous Apollo 8 Earthrise shot.
Beautiful shot.
Oh, yeah, you could just talk about that forever. December 1968, the moon is about 250,000 miles away from the Earth.
Okay.
It takes a month to go around the Earth. It's that far out, it takes a full month to do an orbit. Another shot here of the International Space Station. Instead of being 250,000 miles out, the ISS is only 250 miles out. It's really close. And so it doesn't take a full month for the space station to go around the Earth. It only takes 90 minutes. It's so close, it just whips right around 90 minutes.
Okay.
So weather satellites, there are a number of weather satellites, and there are a number of orbits. The further out you have the satellite, the longer it takes to go around the Earth. And this is important because different satellites have different purposes. So we have a satellite here. This little salt shaker lid will serve as our satellite going around the Earth. Let's say you have a satellite that's 22,000 miles above the Earth. This is kind of a magical spot because at that distance, it takes a full day for the satellite to go around the Earth. Imagine if you put your satellite 22,000 miles up from the equator and had it go with the Earth as the Earth spun.
At the same speed.
Right. The satellite goes around the Earth just as fast as the Earth itself is turning. In effect, the satellite will hover in one spot,
I see.
and it appears when you make a movie loop of picture after picture after picture. You can replay that, and you get these movie loops. Geostationary satellites, these are called. These are stationary in appearance, and they provide a constant frame of reference. We've got an example here. Another nice thing about these satellites, since they're that far out at 22,000 miles, you can see from pole to pole, which is nice. So they're pretty broad view and a constant frame of reference.
So those are the pictures. If you're watching a weather satellite loop on TV, your favorite weather show, that's the picture that you're going to see is one that's sitting over the same spot.
If you're seeing a movie loop play again and again, that came from geostationary satellites. That's the only way you can do that.
Yeah.
The bummer, though, for us in Alaska is we're up on the very top of the planet. And for geostationary satellites to work, they have to be over the equator. So for the geostationary bird to view Alaska, it's kind of like reading a book, but you're reading it edge on like that.
Right.
So there's another kind of orbit called the polar orbit, which is nice. We're near the pole.
Yeah.
And here's a satellite. Those polar orbiters are much closer to the Earth, getting down toward International Space Station elevation. And they're not in the equatorial plane. Rather, their orbital plane is inclined like this. And the Earth turns under that satellite as the satellite orbits. The nice thing about that is for Alaska, the satellite will go right over Alaska a few times a day. And so you get a much closer image. We've got a shot from the Sumi NPP satellite. Specifically, it's a true color image from the VIRS sensor. That's an acronym there. But it's a beautiful shot of Alaska, and you can see so much detail. The kind of detail, because you're close in.
Very high resolution.
You couldn't get this kind of view from geostationary satellites. The advantage of these polar orbiters is nice close imagery. You can see a lot of detail. The disadvantage, though, is that the satellite flies by,
Right.
and then you have to wait a while to get the next image. And if geostationary weaknesses are that you're reading the page like that, the polar orbiter, you're reading the page straight on, but it's so close, and then it zips by, and you have to wait for the satellite to come around the Earth again. So there's no one perfect solution. Different satellites for different orbits, each has their strength, and amazingly, it all comes back to Johannes Kepler and his laws of planetary motion. The same laws that govern how the planets orbit the sun, they govern how the satellites orbit the Earth, and even our little pretend salt shaker right here.
Right, okay. Well, since the 1957 Sputnik, we've been putting man-made objects into orbit around the Earth and starting to get pictures back. Who knows what will happen in the next 50 to 100 years. Amazing
it's
stuff.
A growing science, and the future is bright.
Thank you so much for joining us again, Eric. And for more information on GINA and what the satellite systems do there and what Eric's been talking about today, you can go to the web address on your screen. For Alaska Weather Facts, I'm meteorologist Dave Snyder.